The cosmic ocean, a universe of wonders. Space is incredibly big. It is so vast it's hard to truly imagine its size. Think about the biggest ocean you know, then picture something infinitely larger. Our universe is like that, stretching further than our most powerful telescopes can see. Even light, which is the fastest thing we know in the entire cosmos, takes billions of years to travel across the observable universe. This immense expanse holds countless stars, more than all the grains of sand on all the beaches on Earth. And around many of these stars, planets are likely orbiting, creating endless possibilities for discovery. It's a realm that constantly reminds us of how much there is still to learn and explore beyond our own world. Within this enormous cosmic ocean, there are many strange and truly wonderful things to discover. We can observe giant clouds of colorful gas and swirling dust particles. These are spectacular stellar nurseries, the very birthplaces of new stars and planetary systems, lighting up the darkness with their vibrant hues. We also see entire galaxies, huge collections of billions of stars, sometimes caught in the act of crashing into each other. These are slow, majestic cosmic dances that unfold over millions and even billions of years. These grand events help to shape the overall structure and evolution of the universe as we observe it today. There are also the brilliant remnants of stars that have lived their full lives and then exploded. The distances we talk about in space are simply mind-boggling for us humans, accustomed to earthly scales. We have to use special units like light years to even begin to measure them effectively. A single light year is the distance that a beam of light travels in one whole Earth year. This is a truly huge distance, approximately 9.5 trillion kilometers, or nearly 6 trillion miles. Our closest neighboring star system, Alpha Centauri, is situated more than 4 light years away from our solar system. This means that if we could somehow build a spaceship that travels at the incredible speed of light, it would still take us over 4 years to complete the journey to these nearby stars. Our own galaxy, the Milky Way, is itself about 100,000 light-years from one side to the other. So you see, space is far from being just an empty void or a desolate expanse. It is actually filled with an astonishing variety of matter, with different forms of pervasive energy, and with countless profound mysteries that are just waiting to be unraveled by curious and persistent human minds. Scientists all around the world use incredibly powerful telescopes, some located on high, dry mountaintops, and others orbiting our planet high above the distorting effects of Earth's atmosphere, to peer deep into the farthest reaches of the cosmos. They are constantly finding new celestial objects and previously unknown phenomena. They are tirelessly trying to learn about how stars are born from collapsing gas clouds, how they live their brilliant lives, and how they eventually die, sometimes in spectacular fashion. The universe truly is a giant natural laboratory for us. Introducing the enigmas. What are black holes? Among all the fascinating and mysterious objects scattered throughout this vast universe, black holes are surely some of the most peculiar and awe-inspiring. So what exactly is a black hole, this object of so much scientific curiosity and popular imagination? Try to imagine taking a huge amount of material, perhaps many times the total mass of our own sun, and then somehow squeezing all of that concentrated matter into an incredibly tiny, almost infinitesimally small, and therefore practically invisible, space. This extreme compression creates an object with a gravitational pull so immensely strong that absolutely nothing, no matter how fast or powerful, can escape its relentless grasp once it comes too close. Not even light, the universe's ultimate speedster, can break free. Black holes are incredibly important in the grand scheme of the universe because their powerful gravity significantly affects everything in their cosmic neighborhood, often in very dramatic ways. Their immense gravitational pull can capture unfortunate nearby stars, unsuspecting planets, and vast clouds of interstellar gas and dust that drift too close. As this captured matter spirals inwards towards the event horizon of the black hole, it gets accelerated to tremendous speeds and becomes superheated due to intense friction and powerful compression forces. This superheated material can then shine incredibly brightly across the electromagnetic spectrum, emitting X-rays, radio waves, and other forms of radiation that we can detect. This is one of the main ways astronomers can actually detect the presence of a black hole. How do these strange cosmic objects actually come into being in the first place? The most common way that black holes are thought to form is from the dramatic and violent death of very massive stars. When a truly enormous star, one that is perhaps 20 times or more massive than our own sun, eventually runs out of its available nuclear fuel in its core, it can no longer generate the outward pressure needed to support its own immense weight against the inward crush of its own gravity. The star then undergoes a catastrophic gravitational collapse, caving in on itself with unimaginable force and speed. This violent implosion can be so incredibly intense that it creates what we call a stellar mass black hole. Black holes are endlessly intriguing to scientists and space enthusiasts alike, primarily because they profoundly challenge our current understanding of the fundamental laws of physics. The very theories that describe our universe so well in most situations, such as Albert Einstein's celebrated theory of general relativity, seem to break down or predict nonsensical infinities at the very heart of a black hole. This central point of infinite density is called the singularity. What exactly happens at this singularity remains one of the biggest unsolved mysteries in all of contemporary science. Studying black holes, therefore, helps us to rigorously test the absolute limits of our current scientific theories, pushing us to explore new theoretical frontiers and deepen our cosmic perspective. On the edge of forever, approaching a black hole. Let's imagine for a moment that you are an intrepid astronaut, secured within a very strong and advanced spaceship, and you are undertaking a daring journey towards a distant black hole. What extraordinary and perhaps terrifying phenomena would you witness and directly experience as you ventured closer? As your spaceship gets progressively closer to this cosmic giant, the black hole's gravitational pull would become overwhelmingly, unimaginably strong, far exceeding anything found naturally in our solar system. Crucially, this gravity isn't just uniformly powerful, it's also extremely uneven across relatively short distances. If you were unfortunate enough to be approaching the black hole feet first, your feet would feel a significantly stronger gravitational pull than your head would, due to being slightly closer to the center. This immense difference in gravitational force across your body or across your spaceship is what we call a tidal force. Near a black hole, these tidal forces become extraordinarily powerful. They would exert a tremendous stretching effect on your spaceship, and indeed on your own physical body. It would pull you apart, elongating you in one direction while compressing you in others, much like a piece of spaghetti being stretched. This rather gruesome yet scientifically accurate process is sometimes vividly described by astrophysicists as spaghettification. As you draw even nearer to the black hole, assuming you could somehow survive the tidal forces, you would eventually approach a critical invisible boundary in space. This boundary is famously known as the event horizon. The event horizon is often dramatically referred to as the point of no return, because once any object, including your spaceship or even a beam of light, crosses this invisible line, it cannot ever escape the black hole's powerful gravitational clutches. Not even light, the fastest entity in the entire known universe, can escape from inside the confines of the event horizon. So, if you were to cross this fateful threshold, you would be completely and irrevocably cut off from the rest of the universe. You wouldn't be able to send any signals or messages back to your anxious friends or your dedicated mission control team. Interestingly, for an observer watching your perilous approach from a safe distance far away, something very strange would appear to happen. Time itself behaves in a very peculiar and decidedly counterintuitive manner near a massive object like a black hole, as predicted by Einstein. According to Albert Einstein's groundbreaking theory of general relativity, very strong gravitational fields can actually warp or bend the very fabric of spacetime, the four-dimensional stage on which all cosmic events unfold. This warping of spacetime means that time would pass much more slowly for you, the astronaut bravely venturing near the black hole, compared to someone observing you from a region with weaker gravity, like back on our home planet Earth. If you could somehow survive a close encounter with the event horizon and then manage to return to a safer distance, you would discover that much more time had elapsed for everyone else in the universe. Unlocking the secrets, the future of black hole research. Scientists around the globe are working diligently, using their collective ingenuity and the most advanced technology available, to solve the many profound puzzles that still surround the nature of black holes. They utilize incredibly powerful telescopes, both ground-based observatories strategically situated on high, arid mountaintops to minimize atmospheric distortion, and sophisticated instruments orbiting our planet high up in space to observe these enigmatic cosmic objects across the entire electromagnetic spectrum. A truly monumental breakthrough in this challenging field of research occurred in the year 2019 with the public release of the first ever direct image of a black hole's shadow. This historic image, captured by the International Event Horizon Telescope collaboration, revealed the supermassive black hole residing at the heart of the distant galaxy Messier 87. This remarkable and widely publicized image was a stunning visual confirmation of Albert Einstein's detailed predictions about how black holes should appear if we could somehow see them, further cementing his revolutionary theory of general relativity. Such direct observations, along with many others that study the intense light and various forms of radiation emitted from materials swirling furiously around black holes and accretion disks, provide invaluable data for researchers. This data allows scientists to rigorously test their complex theoretical models and to continually refine their understanding of how these extreme objects behave and how they profoundly influence their surrounding cosmic environments. Another incredibly exciting and rapidly advancing area of active research involves the detailed study of gravitational waves. These gravitational waves, which are like invisible ripples propagating through the very fabric of space-time itself, were also predicted by Albert Einstein more than a century ago, but they were only directly detected for the very first time in late 2015. This groundbreaking detection was achieved by the dedicated teams working at the Laser Interferometer Gravitational Wave Observatory, LIGO, in the United States, and the Virgo Interferometer in Italy. This monumental discovery effectively opened up an entirely new window onto the universe, allowing us to listen to the most violent cosmic events, such as the cataclysmic merger of two massive black holes or the collision of dense neutron stars. By carefully analyzing the intricate patterns of these faint gravitational waves, scientists can deduce crucial information about the black holes. Despite these amazing recent advances and the wealth of new data, there are still many fundamental and deeply perplexing questions about black holes that remain unanswered by current science. For instance, what truly happens to all the information that is contained in matter that falls into a black hole? Does this information simply disappear from the universe forever, which would violate some known principles of quantum physics? Or is it somehow preserved or perhaps encoded on the event horizon in a way we don't yet understand? This is famously known as the black hole information paradox, and it represents a major point of ongoing debate and intensive research among theoretical physicists worldwide. Ultimately, understanding black holes is absolutely crucial for the advancement of science because they represent the most extreme environments in the cosmos, pushing our theories to their breaking points and guiding us towards a more complete picture of reality and the universe's deepest laws.